Hello, I am Dr. Deanna Hintz, and I'm an assistant professor at the University of Illinois Department of Atmospheric Sciences. In this video, I'll be talking about remote sensing and how we use it to study our climate. Remote sensing is taking measurements of something that you are not directly in. We can use the radiative properties of the Earth, atmosphere, and the ocean to study our climate system with remote sensing. It's easiest to measure what's happening to the climate system from space. And so we have a lot of satellites that are constantly taking measurements of our climate system by taking advantage of how radiation interacts with the planet. There are two primary satellite orbits that we use: low Earth orbit, or LEO, and geostationary orbit. These orbits determine whether a satellite is scanning a piece of the Earth as it zooms around at high speed, such as an LEO, or if it's able to constantly measure the same area of the planet, as in a geostationary orbit. The main difference between the two orbits is altitude. LEO occurs below 2,000 kilometers in altitude, whereas geostationary orbit happens at approximately 36,000 kilometers. Satellites in LEO typically make it around a planet quickly and see a sunrise every 90 minutes or so. Although many LEO satellites orbit from pole to pole, some of them have lower inclination angles, so they can focus more frequent observations over a particular latitude range. Geostationary satellites orbit at the same speed as the Earth's rotation and stay over one spot, and thus experience sunrise at the same time the point below it does. On board these satellites are a variety of remote sensing instruments. There are two kinds of remote sensing. The first is passive remote sensing, where you are measuring whatever comes the instrument's way. Passive remote sensors measure most of the wavelengths of radiation we commonly see, such as the long-wave radiation emitted from the Earth's surface and clouds. The second is active remote sensing, where you are emitting radiation from the instrument and measuring the properties of the radiation that makes it back. In active remote sensors, we send out microwave radiation to do everything from measure how fast you're driving your car to telling us how much rain is in a cloud. The majority of remote sensing from satellites uses passive remote sensing instruments. Typically, these instruments are sensitive to a particular band of radiation wavelengths, and those bands are related to radiation from a particular source. On geostationary platforms, such as the United States GOES satellites, three types of sensors are common. A sensor that measures the visible light being reflected off of the planet, almost like taking a picture with a camera. A sensor that measures the infrared radiation being emitted from the Earth's surface in the clouds, almost like taking a picture with a heat camera. And a sensor that measures the wavelengths of radiation emitted by water vapor in the atmosphere. Since most of the atmosphere is invisible to the wavelengths picked up by the other two sensors, you can use the water vapor as a tracer for how moisture is moving around with the larger circulation of the atmosphere. Because these measurements are geostationary, you can create a climatology for a particular location of how these variables change over the course of days, months, years, or decades. Many LEO satellites carry sensors that take similar measurements as geostationary satellites, such as NASA's Moderate Resolution Imaging Spectroradiometer, or MODIS, but with a trade-off. Because of the lower altitude, they can take measurements with greater resolution, but because of the speed that they're moving, they only capture snapshots over a particular location. A variety of passive sensors have been deployed on LEO satellites that currently can't be on geostationary satellites. Infrared sounders, such as the Atmospheric Infrared Sounder, or AIRS, use emitted infrared radiation from different gases in the atmosphere to determine vertical profiles of temperature and water vapor. Microwave radiometers, such as the Global Precipitation Measurement Microwave Imager, or GMI, measure microwave energy emitted from clouds and precipitation, which creates a climatology of global clouds and precipitation. Using various combinations of wavelengths and viewing angles, other passive remote sensors are used to track climate-relevant properties such as changes in land use and vegetation, sources of pollution and aerosols, changes in sea ice, and the presence of large forest fires through carbon monoxide emission. A huge advance in remote sensing was launching active remote sensors into space. The Tropical Rainfall Measurement Mission, or TRMM, carried the first precipitation radar in space, and CloudSat was the first cloud radar. These satellites created a more accurate description of tropical cloud and precipitation distribution and structure, which led to a much better estimate of the global energy and water cycle related to precipitation. The Global Precipitation Measurement Satellite that launched in 2014 extends these measurements into the mid-latitudes. This is an exciting time to be using remote sensing measurements to understand the climate. Remote sensing measurements have been used to directly study the Earth's climate and have been integrated into global climate models to improve their predictions. As our understanding of the Earth's climate system becomes more complex, remote sensing will always play a key role in obtaining the necessary measurements to ground our understanding in reality.